Oh, this is the one that I went through very quick. Jumped to problem number 9. Okay, I'll give you some time to work this thing out. Right? This is the time for you to work this thing out. And I think in the meantime, Ellie and I will go off and have a cup of coffee. Let them struggle.
How many minutes are we going to give them? 5 minutes or so?
We'll give them about 4 or 5 minutes. So they stop at, say, 10:27.
Stuart Camp, do you want to ask something? I see your hand is up.
No, sorry, ma'am. I forgot to take my hand down. Sorry.
Not a problem. Marcus Taliak, I see your hand is raised as well.
All right, let's resume. There were a few people who put their hands up and they gave me their answers in the chat column. I think all the answers that I saw were correct. And one of the persons there was Mulindani. Can you please tell us how you got an answer, Mulindani? You said the answer was 405, which is the correct answer.
I got got the answer 405 by first starting off with a formula of n bracket n minus 3 bracket. And then the n being the number of sides of the polygon. So 30 multiplied by 30 minus 3.
But that doesn't give you 405.
Say I'm still getting there. And then we multiply that, and then I got 810. Then I divided it by 2, which gave me 405.
So your formula is not n into n minus 3, but it's n into n minus 3 over 2.
Yeah.
Okay, so she used that formula. Right. Okay. Anybody else wants to take a bash at it? She used a formula. Now this is a very unknown formula. If you go and Google it or whatever, you probably will get it, but it's not in the syllabus. So if you know it, that's well and good. Then you can get straight to the answer. Anybody else wants to take a bash at this? Explain.
Prof, I had a different answer.
Yeah, what answer did you get?
So, a 30-sided polygon, if you pick a point there, you cannot count the diagonals for the two sides. And so then, it would be 28 times.
Now, wait a minute. You see, you got a point here as well. It's not 28. Think carefully. You're not allowed to take that point for a diagonal, right? That's what you're saying. And you're not allowed to take that point for a diagonal. And you must eliminate that point there as well.
Oh, I forgot about that. That's why I had a different answer.
So therefore you
then ended up with 14.
27.
I ended up with 14.
Okay, so you got 27 diagonals shooting out from each point. Right? Because you're not allowed to, sorry, I'm using this bad thing here. So if you start at any point and try to draw the diagonals, you have to eliminate 3 points because the two adjacent points together with that point itself cannot be counted. 3 points have to be eliminated from 30. So you can draw 30 different diagonals from each point. Right? I'm sorry, 27 different diagonals from each point.
And then I divided by 2 because there will be some repeats.
What do you mean by some repeats? If there are some repeats, why do you divide by 2 and not by 5? Alright, so from each point, you've got 30 diagonals. So on the surface, it looks as if you got 30 times 27 diagonals. This is what Neni said. She used a formula for that. But we are trying to count the total number of diagonals. If you take this diagonal here, suppose this, you extend this line here to its, take this one here. You can see it clearly. At this point here, you count this diagonal. But when you come to this point, you're counting the same diagonal again. In fact, you count each diagonal twice. Because when you come to there are 2 endpoints. Each time you come to the endpoint, each endpoint creates the same diagonal with the other endpoint. So you are counting them twice. So really, you have that these come in pairs now. So the 30 times 27 pairs of diagonals, not diagonals. Right? That is the important thing. So you have to divide by 2 to get 405, which is the answer. Okay, my thanks to all those who have contributed. Thank you very much. The answer is 405. We go down to the next problem. Now this problem here, I would be very, very surprised if anybody got this problem out on their own without looking at the answer. It's quite a tough problem. So let's just look at this problem, and I purposely put this to show you that geometry, although something looks very harmless, like this problem here, you've got a nice triangle, you got a point inside it, and you got, you know, the 4 angles given, and you're asked to calculate one of the angles. It looks very easy because you just know the sum of the angles of a triangle is 180 and so on, and you try it. And then you see to your dismay that none of these, no matter how hard you try, you cannot get to angle AOB. So let me just get to so the problem is to calculate angle AOC. This is the thing that you need to calculate. And when you try to do this with the given information, you wouldn't get anywhere. Right. Now the fact of the matter is, one can actually prove in this thing that AO equals AC. That this is an isosceles triangle, and it takes a while to get there. So let's just eliminate the mystery, and I will show you how you can prove that AO equals OC. The moment you do that, then immediately you can see that this is an isosceles triangle. This is 30 degrees, the other two add up to 150, and that will be 75, which is the answer. But to get to that, I need to show that AO equals OC. Okay, so to that end, I've drawn the diagram here again. And what I've done is this is an example where you have to draw constructions. In fact, in many of the Olympiad problems, you need to draw some new lines. We've already seen that. We saw, for instance, in that quadrilateral, to find the area where we got 31, we have to draw a line which wasn't there, the diagonal. So very often you have to draw new lines to solve your problem. They are called constructions. In all the theorems, you've got constructions. Every theorem has got a construction. But normally in a high school, they don't give you problems with constructions, right? Because they are more advanced. But for the Olympiad students, construction problems are quite prevalent. In this case here, there are quite a few constructions, and I will tell you what motivated me to get to these constructions. See, when you look at 15, 15, now that's, they add up to 30. Well, that is already 15. So that is 15, that is 15. So you have an isosceles triangle here. Okay, so you have an isosceles triangle. An area, I told you, when you got an isosceles triangle, a useful thing to do will be to join the vertex. It lies on the perpendicular bisector of the other side. I recall I said that when I draw a perpendicular to this line, it will bisect it. So let me do that. Now I'll tell you why. Okay, just hold on with that. Then the other thing that I do is, I see I got a 15 and a 30. These are all nice angles. They don't give you 45 and 30. They all come to nice angles. They're not sort of random angles. I actually draw the height of this original triangle and produce it. So I've got several constructions here. I've got this is joined, that is extended, this point is joined to that, and that point is joined to that. The whole idea is to, see, when I do that, I'm trying to prove that this equals this. right? So what I do is I make this the hypotenuse of a right angle triangle, as we've done here now. This side here, and that one also, it becomes the hypotenuse of a right angle triangle. Okay, and if I can show that these two triangles are congruent, then I have that these two are equal. Are they congruent? Well, I've got 90 degrees. 90. Both of them are right angle triangles. One down, two to go. We got that this is 15. This angle here is 15. Now we can actually calculate this angle here, because this is 30, you see. And this is a right angle triangle. The whole big thing is a right angle triangle. So if this is 30, this entire angle is 60. And these two add up to 45. The whole thing is 60. So this is also 15. Right, so that's fantastic. You've got these two angles are the same. And you've also got sorry, just ignore that phone call. So I've got one angle and two angles. That's all I've got. I don't have a side. I need to have a side. Now, how do I get to a side? Now, let's watch this carefully. A very important fact in a right angle triangle. Now watch. I'm going to tell you something that you must remember, because it's very useful in lots of situations. When you got a right angle triangle, right, and you take the midpoint of the hypotenuse, in a right angle triangle, there's a beautiful result which says that when you join this thing here to this line is the same as that one. There are three lines which are equal, right? When you join this, these are equal. Okay, and it's a very interesting result that the midpoint of the hypotenuse, right, it's actually the center of a circle that goes through the three vertices. See? So these all become radii. So the midpoint of a right angle triangle, the hypotenuse of a right angle triangle, is the center of the circle which goes through three vertices. Right. Now, some of you may want to know the proof of this. The proof is, quickly I'll give you. There's a construction to prove this thing. Right? Let me just draw this elsewhere so I don't. I'm attempting to rush now and I don't want to do that. So the goal is given the scenario, right, I want to prove that this line here is a single stroke. So how do I go around proving it? The proof is as follows. There's a construction here, and the construction is from this point draw a line which is parallel from that line you draw a line which is parallel to the other side. And there's a theorem in geometry which is like a midpoint theorem, and that says that if you got the line joining a point, the midpoints of two sides of a triangle is parallel to the third side. Those of you who are familiar with this will know that we can now conclude that these two are equal. Go and read the midpoint theorem to understand why we can make that conclusion. This is actually the converse of the midpoint theorem. It's called midpoint theorem. Right. Now, because it's parallel and this is 90 degrees, that has to be 90 degrees. And lo and behold, you've got that this line, this red line, is really the perpendicular bisector of this line. And I told you that any point on the perpendicular bisector is equidistant from these two. That allows you to say that these are equal. All right. So here I got this right angle triangle here, and I got the midpoint of the side, and that is why I joined it to this, you see. When I joined it to this, now I know that this thing is also single stroke. Okay? And now you got an isosceles triangle here. Because this is, these two are equal. DA equals DE. I've just proved it. So therefore we have an isosceles triangle. And you already have one of the angles. What is the angle equal to? 15 plus 30 plus 15. It's 60. Oh, now that's a great thing. Because this is just not an isosceles triangle. It's an equilateral triangle. Because that is 60. This will have to be 60. And that will have to be 60. So it's an equilateral triangle. So I can put a stroke here. And I have the third condition, that these two triangles are congruent. Starting with that stroke, I can land up with this stroke. See? And now I've got one side and two angles. These two triangles are congruent because of that. And therefore, the hypotenuses are equal. That makes this triangle isosceles. And that allows you to conclude that the angle is 75 degrees. So you can see there's a lot of things that went into the calculation of that angle. If I went a bit too fast, go and look at the book. The problem, the name of the problem is given, the number, and just go and have a look at that in the book. Problem 290. So you go to the book and control find in the book, and then you type S290. Remember, don't look for 290. When you're looking for a problem 290, you type P290, and when you're looking for a solution, you put S290. If you type S290, you'll get straight to the solution. And there are 2 or 3 solutions. Some of them are trigonometric solutions and other solutions. I think I got about 3 solutions. Very, very informative. So you are well advised to go and study that, especially those people who are in grade 12, right? And you will get a lot of insight into geometry by studying this problem. So this problem was really meant for those higher order learners. Okay, any questions?
That's pangs that. Oh,
Was that too much for you?
that was tough.
Mind-boggling. But when you look at that, you see the power of geometry. Well, not just the power, the depth of geometry. Sometimes some problems are very difficult. You know, so there are some problems that people a lot of time to actually solve, although they look easy, right? Like this one here. It's a good example. All right, now we go on to problem 11, which says, this is the question. So you don't have a picture here of a quadrilateral, so let's just draw a quadrilateral. Oh, better get my... Let me draw it something like that. Now we have a quadrilateral. Let's see what the question is. what is the biggest possible area of a quadrilateral? The four sides are given. Didn't I do this problem?
Did, Prof.
I did, isn't it?
Yeah,
You
and
have,
there was a
Prof,
similar
yes.
one.
I recognize this problem. Okay, let me not
Yeah,
do this
we
again.
make them triangle.
Yeah. Okay, let me do this. I don't know how this problem sneaked in here, but thanks for confirming. I recall explaining this problem. So let's just get out of this problem and go to the next one. Okay. Now, this problem here is an interesting problem. Two vertical sticks in the ground have lengths 2 meters and 3 meters. The top of one stick, these are your sticks, and the top of one is joined to the bottom of the other, and this is joined to the bottom of this. They meet at a point P. They say, what is the point height of P above the ground? Now, this is very interesting because it's not telling you how far the sticks are apart. The problem suggests that it doesn't really matter how far they are apart. I could have them a kilometer apart for all we care. And you got a stick which is 2 meters long, another one which is 3 meters long. And then we join these. Woo! All right, just imagine that's a straight line. And then where they meet, the question is, that point it meets, it's a certain distance above the ground, and it's the same as this one here. Because the question says, what is the height of P above the ground? As though it doesn't matter what the distance is. So that's very interesting. Now we have to see why that is so. So we get an interesting situation. So let's draw the height, because there's mention made of the height. So we'll draw it. And okay. And let us give a name to that height. Call this H. So you got, these are 90 degrees because they are vertical to the ground. Now we need to calculate this H. That's the unknown. All right, now, you know, when you got triangles and you got sides, lines which are parallel to it, there are very important theorems in geometry which deal with that. I'm going to say that all over again. If I've got a triangle, and I got a line which is parallel to one of the sides, there are some very important conclusions. Okay, the midpoint theorem is an example of that. But in general, if you got any line which is parallel to this, you can make some very interesting conclusions. So, the first conclusion is that these sides are divided in the same ratio by this parallel line. If this is 2, and if this is 3, if the ratio is 2:3, and if that is 4, then this will have to be 6 to get the same ratio. So this over that, that's the ratio, the same as that over that. So that's a very important conclusion. You can also have the conclusion that this over the whole thing equals that over the whole thing. Right? And in that case, this over the whole thing, over that over the whole thing, is actually equal to this over this. Okay, all these conclusions will be obtained when you do this thing called similar triangles. There's a whole geometry regarding two triangles which are not congruent, but they have the same angles. Three angles is not a condition for congruency. So they say, okay, if you've got two triangles which have got the same angles, what can we say? They're not congruent. Right? One is a photograph of the other. This guy here is just a diminutive version of the big guy. Right? So there's a contraction. The sides are all contracted in the same way, as it were. Right? So whenever you've got a line parallel, you have this situation. So now that allows me, you see this bottom line. Suppose this distance is D, right? This distance between the bases. So then if this is X, I've got lots of symbols here. If that is X, then D, this has to be D minus X. So I've got a lot of things named, right, in this picture. And I now suggest that we can actually calculate H with all this, and using the fact that you got similar triangles. Now, where are the similar triangles? See, if you look carefully, you got to watch my pen. Comes down, 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 and there you got a parallel line to this. Hope you can all see this. In this right angle triangle, you got a point P here. You're drawing a line parallel because it's 90 degrees here, all this 90 degrees. Okay. From what I told you just now, it means that H over 2, that over that, is this D minus X all over the whole thing, which you said was D. Okay. And also, if you look at this other triangle on this side, you have a similar scenario. There's also a right angle triangle here. Again, you've got a line which is parallel to this. Okay. And you still got H here, but you've got 3 here. So here we can say H over 3, H over 3 is equal to this piece, X, over the whole thing. The whole thing is D. So the similar triangles where the sides are in the same ratio helps us to conclude these two equations. Now watch how I can destroy the X and the D's, because those guys, we don't want them. The way to do that is to add these two equations. You have magic. They both got the same denominator, D. The numerator is D minus X plus X. Goodbye, X. Bye-bye, nice to have known you. And you got D over D. Ah, goodbye, D. Nice to have known you as well. You got 1. So you got one equation with one unknown, namely H, and you can solve it. I'm not going to do it. No, but you can just, okay, I'll do it. You multiply by 6 right throughout. You get 3H plus 2H is equal to 6. Right? 5H is equal to 6. And H is equal to 6 over 5, which is 1,2 meters. So this thing here is 1,2 meters, no matter how far apart they are. Okay, so that's a very interesting problem, which is quite informative also. And you see, although you got 3 unknowns, I've brought in so many unknowns here, 2 of them disappear very conveniently, but you have to know that when you come to this, you must add them, and that will destroy the X's and the D's. But that is what happens. When you solve equations, you try to get rid of unknowns. So that destruction, merciless destruction, goes on quite ruthlessly in the subject called geometry, or algebra for that matter. Cancel. All kinds of cancellations take place. Okay. Number 13. Is there anybody who has tackled this problem and they want to tackle it?
Prof, I think I have an answer, but I didn't think of it in a mathematical way.
Oh, you didn't.
It's
Okay. So what was your
my answer
reasoning?
was 1:2.
Oh, 1:2. Huh?
I tried to divide the whole thing into tiny triangles,
Oh yeah.
and then I found that A consists of 2 of 4 of the triangles that B has. So then I simplified it to 1:2, but it's not mathematical.
Yeah. Well, that's quite okay. The only thing is, you might have assumed that these squares. Oh, okay. Yeah, somewhere along the line, you might have made an assumption. That answer is wrong, by the way. Okay, you made some false assumption which allowed you to come to a wrong conclusion. Anybody else tackle this thing? At least we got one person who tried it, which was quite encouraging.
If
All
we
right.
label the sides X,
Can you say that again, please?
so if you label the side of the big square X,
Okay, the entire side.
yes, entire side X.
I don't like that. I'll tell you why. Because then you're going to have fractions, right?
Yeah.
You try to avoid fractions. If you want to do that, then you might as well name this thing here X, so that becomes 2x.
Okay.
Right. All right. If you say
So
this is x,
the area of B is equal to X squared.
yeah. The area of B is x squared.
Yeah. The length of the diagonal then becomes. What is this?
Okay, you got 3x here. So let's look at the diagonal. We'll call it D. D for diagonal. That's this diagonal here you're talking about,
Yes.
right, is equal to that squared plus that squared. So if this is x, then that is 2x. So you have 3x altogether. So it's 3x all squared plus 3x all squared.
Why would it be 3x? Would it not just be 2x?
Because this is the diagonal. Oh, I'm looking at the large square.
Yes.
Oh, I see. I'm looking at the large square. The diagonal is this whole thing. And that's the hypotenuse of this right angle triangle. And this side here is 3x.
How did you get that to be 3x? Would that
2x
not
plus
be
x.
X for the length of
Oh,
the
I'm sorry. Where did this 2 come from? Why did
I
I?
think you labeled the whole side as 2x.
Oh, the whole side was 2x. Oh, Godfrey Daniel. All right, let's that's terrible. Okay. Okay, so what we are saying is that, yeah, this equation is wrong. Okay, continue.
But then that becomes the length of the diagonal then becomes 2 root 2x.
All right, so we are saying that this is x, and this is x.
Yes.
Yeah, but this will be x, isn't it?
Yes.
Right.
That
Okay,
will
that'll
be
be x. Right. Okay, so, and this is x again.
Yes.
X again. So d squared is 2x all squared multiplied by 2. This 2x squared, so that gives you 8x squared. So d squared is 8x squared.
Yes.
All right.
So then we can find d.
We can find d. D is equal to,
2x.
maybe you can just say x times square root of 8. All right.
Okay. And then we know the side length of a has to be that divided by 3.
Why 3?
So for a, we can fit 3 units by inspection.
The side of A is that divided by 3.
And then we take the square of that.
And that will be the area. Area of A is the square of the side, which is d squared over 9.
And then you can
Actually 9x squared.
Yes. Then you can substitute back in.
Yeah, so you get 8x squared. Eight over 9.
Yes.
Okay, now that's very nice. I just wanted to know why you said that the side of this is d over 3.
Oh, okay. So when I did this, I worked with the whole side being x. And from there, you can see that x and x will give you. So, oh, hold on.
Okay, let me help you along. I think this is what you did. That's correct, by the way. So let's just give another name to it. Let's call this y here. Right? That's the side of the square, right? Now, what is important is that this angle here is 45 degrees here,
Yes.
because this is a diagonal of a square, you see, and a diagonal, it bisects the corner angle of a square. So therefore, this will have to be 45. So this part here will have to be y. This is an isosceles right angle triangle. Now this is a square, so this part here is
Also.
will have to be the same as y, and by the same argument, this will have to be y. So the diagonal is y plus y plus y, which is 3y. All right, so that is how he gets that this thing here, the diagonal is 3 times this, right? And then after that, the rest is as you said. Thank you very much. It wasn't an easy problem, and you got the right answer. Okay, I would have done it almost the same way as that, but I would have called this x and y rather than go through all this. Get two unknowns, and eventually you will substitute, and you'll get to the answer. So the ratio of area A to area B is y squared of x squared. So you have to remember that this is the goal. You need to calculate y squared of x squared. That's the area of. So if you let the side of this be x, let the side be y, and then try to make the equations as you did, and eventually you get y squared over x squared. Okay. Now it's 5 minutes past 11, and we are at problem 13. I think some people, if you want to go away, that's okay. Let me just pause here. Okay, so quite a few people went off. Ellie?
Yeah, we now have 58 participants.
Yeah, I would like to just go on for another maybe 10 or 15 minutes and do these. If people want to go, they can go. But there are 58 people who are interested in staying on. So I'll carry on. Is that okay?
You think if we go on for another 10 to 15 minutes, I don't think we'll be able to cover all the problems.
Well, we'll try to cover the problems. Right.
Okay.
Okay. We'll try to cover it. It may take more than 10 or 15 minutes. Okay. I see there are some people at the chat column. What are they saying?
They're just asking about the e-books. I did respond that I should make contact with David, who can track the delivery, so we can continue to the next question.
Yeah. There is a link directly to the sales house of SAMF. If they get that link, they can go straight to the section rather than go through the SAMF website.
And that won't be possible because then they need to buy the book.
Oh, I see. Yeah. Now I'm talking about people who ask me how they can buy the book, I usually send them that link.
Yeah.
Okay. All right. Okay. Then thanks guys, whoever here for remaining behind. We'll try to do the rest of this. You would see that you will be greatly benefited by being here. All right. Now, the next problem. Okay, this is a very unusual kind of a problem. We will hardly get this problem coming out in Olympiad, but I thought let's just put it in. It'll be useful for them with a little bit of trigonometry to get some insight into this and maximum and so on. So there's some good ideas here. All right, let's just read the question. The question says, suppose x and y are two numbers in the interval between minus 90 degrees and plus 90. In other words, these are angles which are between bigger than 90, negative 90 and less than positive 90. And you've got that tan x is equal to cos y. The question is, what is the greatest value of x? Right. All right. There's a little bit of insight into this. Okay. Now, see, to get the greatest value of x can be, you see, tan x. It assumes a lot of values. If you know the graph of tan x, let me just do this. If you know the graph of tan x, the graph of tan x looks something like this. Like that. So we have that as x gets bigger and bigger, the tan x, that's a vertical line, gets bigger and bigger. So as x gets larger and larger, the tan x gets larger and larger. And if you look at cos too, the same kind of a thing happens with cos. Not quite with cos. What happens with cos is the following. The graph of cos x between minus 90 and plus 90 is like this. And then it goes down like this. Right. Now, tan x cos y, so y's are here and the x's are here. This is your tan x and the cos y. So let's find out cos y. The largest value that you can get for cos y is what? It's 1. Right? At 0 degrees. When y is 0, then cos y is 1. That's the largest value. All the other ones are smaller. You can see by the graph. All these are smaller than 1. So the largest value you have cos y is 1. What does it mean? It means that tan x is less than or equal to 1 because cos y is less than or equal to 1. So now the question is, what is the largest value of x for which tan x is less than or equal to 1? So you look at this, there's your x's here, and when tan x is equal to 1, you want to know when this part here is 1, what is that? Tan x must be less than or equal to 1. So x must be inside here, which is the largest possible x. Now tan x equals 1, right, with your knowledge of, trigonometry, x must be 45 degrees. See, because tan of 45 is 1, and all the other ones less than that will be smaller than 1. Okay, so you see the largest possible value of x is 1, but there are other values which are bigger, but you want cos y. You see, cos y is less than or equal to 1. So that's a kind of a sort of advanced graph question, but hopefully some of you would understand the way graphs work by looking at that solution. And I'm not going to spend much more time over that. Let's get on to the next problem. This is the only one where we have trigonometry. In fact, these Olympiad problems rarely test trigonometry, only occasionally. So, and certainly not in, hardly ever in round one. Okay. I'm going to skip this one here. You could try this one because we don't have so much of time. If you don't take too long over the others, then I'll come back to this. I'm interested in this problem here. Okay, even before we go do this, let's look at the last problem because it's the easiest one. Anybody wants to argue this out?
Prof, there are 365 days in a year, so if there are more than 365 students, that means there will be more than one people with a birthday on a particular day.
That is correct. And you have to
Yeah,
think
you
about-
just use pigeonhole theory.
Yeah, well, without using any languages, you just ordinarily, when you look at this thing, you got there are 365 days in a year, and you got 370 students. So, show that at least two of them have birthdays on the same day. At least two of them. All right. That's right. It's kind of obvious, but one of the ways of proving it, when you're proving things, you use mathematics to prove it. This example is a good example where you can prove by contradiction, right? And you say you got 365 days in the year. Right? So suppose we line up all those 365 days along a straight line. And we say, suppose that this is false. Suppose this is false. At least two of them have birthdays on the same day. Suppose that is false. It means that on each day you can't have two. You can't have two birthdays falling on any particular day. So each day you'll have either no birthdays or you'll have one birthday. Right? So these dots, there are 365 dots altogether. And you're adding a number of numbers which are either 0 or 1. That's one of the ways of looking at it. When you add that, what's the largest possible value you can have? Right? The largest possible value you can have is 365 when all of them are ones. Right? And that's impossible because you've got 370 students and you need to put in 370 students at each day. Everybody has got some birthday. Right? So this is an argument where you prove by contradiction, or they use what they call the pigeonhole principle, as somebody said, and that says that if you can regard these as pigeonholes. In other words, pigeons are flying in here, right? And there are 370 of them who are flying in. Right? They all can go in here and occupy different houses, but there will be 5 guys will be left behind in the cold, right? And they'll say, what the heck, I have to get into one of these houses, and that forces those houses to have more than one pigeon, right? Which is the same as saying some day has got 2 birthdays. I mean, some day has got 2 students. 2 students have the same birthday. Right, so that's an illustration of the pigeonhole principle. Okay, the next, or just ordinary proof by contradiction. The next problem we can look at is, I think this one here, it might be easier. Yeah. Try this. It's a very easy problem actually. Okay, anybody wants to take a go at this? So what is the probability that at least two adjacent red faces? So three sides are taken at random. What is the probability that at least two adjacent red faces? So let's just paint one of them. For example, the top face. Now we want two adjacent faces to be red, right? So take a second one. Second one is going to be anywhere. Okay, suppose at the worst case, you painted this red and you don't want any red faces. I'm sorry, you painted these faces and you don't want two adjacent red faces. In other words, you don't have two crooks who are standing next to each other. Right? Two red faces. Okay, so then if that is red, then all the sides around here, none of them can be red because they're all adjacent to this. Then you have only the bottom face can be painted red. Okay, so the bottom face, if you paint it red, now you're about to paint the last one. So once you paint two red faces like this, now you'll notice that the last face has to be next to two of them, you know. So you'll always have adjacent red faces. That's the conclusion. The conclusion is that there will always be no matter how you look at it, always be two adjacent red faces. In the language of probability, when you say something always happens, it means that the probability is 1. Something always happens. If something does not happen at all, the probability is 0. So this is, probability is a number between 0 and 1. If it doesn't happen at all, its probability is 0. It always happens as 1. And then you have some number which is in between, which gives you the chances of something happening. Right? It's some kind of a number between 0 and 1. Okay, so in this case here, the probability, the answer to that question is, the probability is 1. Okay, so these two are relatively easy questions. Now let's get on to this one that I saved for the last. So here you have a box contains P white balls and Q black balls. Okay, let's just draw the box so that we have a picture of what's going on. You have P white and Q black. What else does it say? It says the two balls are chosen at random. So you got, let's just separate them. You got P white and Q black. So two balls in the box are chosen at random and are taken out of the box. So when you take two balls out at random, then it says here that if they have the same color, then a black ball is put into the box. If they got the same color, then a black ball. The black ball could be from the outside. There's a large pile of black balls outside. So something from the outside is put into the box. Right? If they are both white. But if they're both black, then you can take one of them and put them back into the box. Okay. Now this problem here, it's not an easy problem. But what we do is we're going to assume that at any given time, you've got X white balls and the white balls black balls. At any given time, you got X white and B black. Right. Now suppose this is the scenario somewhere. It starts off with P and Q. So after doing these things, carrying out the experiment, you come to some stage and you just call it X and Y. Now there are several possibilities. When you take out these two balls which are chosen at random, like you could have white, or you can have black, or you can have white, black, or you could have black, white. Oh, same thing. Okay, you can only have those kinds of situations. Now what happens here? We have X comma Y here. X white and Y black. Right. Now, when we see this happening, two whites, they both have the same color, then a black ball from the pile is put into the box. So what happens is a black ball, so X remains as it is, but the Y becomes Y plus 1. I hope you understand what I'm saying here. Right? When this situation occurs, the number of black balls increases by 1. Right? Nothing happens to the white balls. Now if you got in this situation here, if they both have the same color, then a black boy so even here you have X, they both got the same color, so you have that situation. Now in this case here, you got a white ball and you got a black ball, so now they have different colors. Right? If they are the same color, then black ball is put into the box that we've done. But if they have otherwise, the white ball is put back into the box. So what happens here is that, oh, I'm sorry. We should have I beg your pardon, just hold on. I had an error here. There are two processes here. Let me just get this thing right. Okay, so we had XY. Now watch. Two white. So what happens? the x became x minus 2. That is what I wanted to say. The x became x minus 2 because those two were chosen and the y remained the same. Right? And now, both y's, and then what did we say? We wanted the y to increase by 1, so you got x minus 2 and you got y plus 1. This is what happens in this situation. In this case here, you got two blacks, so the two blacks were taken, so the y's were reduced by 2. And in this case, what happens is that the black ball is put in, so that you got x here, and this is increased by 1, number of black balls. So it becomes y minus 1. The number of black balls becomes y minus 1. And in this case here, what you have here is that one black ball and one white ball have been removed. And when we see this, what do? We increase, the white ball is put back into the box. So the one white ball is put back into the box, and you have the x minus 1 becomes x, and nothing happens to the black balls. Now this is the situation. After each draw, the number of white balls, watch, number of white balls either reduces by 2 or remains the same. The number of white balls either reduces by 2 or remains the same. You see? So, the number of white balls, now the question is now, what is the probability that the last ball is white? Now, if the last ball is white, so each time you take out 2 and you put 1 back, right? So the whole thing keeps reducing by 1 because you take out 2 and you put 1 back. So eventually you will have that these things, will come down to 0. But you want to know what is the probability the last ball is white. If you want this to be W and that is 0, right? What is the probability that that happens? The answer is that this can only happen if, you see, the p is kept reducing by 2. So originally you had p, and they kept reducing by 2 until they came to 1. So what it means that p must have been odd at the starting point. See, so the probability that p is odd, the random, is 1 in 2. Either p is odd or p is even. If p was odd, the last ball is white because you're taking them off by 2. But if the p was even, then you're taking them 2 at a time, and eventually you'll have that this is 0 and the black ball will have to be 1. See? So the answer is, the probability is a half. It's the same as saying what is the probability that p is an odd number? That's the question. What is the probability that p is an odd number? And the answer is, take a random number of white balls, the probability that this odd number is, it's either odd or even, so it's a half. Okay, I think we've exceeded this by half an hour. Maybe I'd better just finish this last question, which I avoided. Look, I admit that these questions are quite hard. That is why I'm not asking you to do it as an assignment. I am doing it for you. The idea is to teach. I want you to be exposed to challenging problems, and I'm giving you strategies on how to solve them. Right? So when you come to these classes, you have a lot of experience to see how you can solve some of these problems. They're seemingly difficult, but at the end, when you see the solutions, you say, Well, I think I could have done it. And that's the important thing. Even if it's hard, it's not something that you don't understand at all. That's the important thing. So here you got one of the factors of 48 is chosen at random. What is the probability that it is not a multiple of 4? All right, okay, then it's one of the factors. So you have to write down all the factors of 48. Now 48 is equal to 8 times 6. Let's write this in as prime powers. That is 2 cubed times 2 times 3. And that is 2 to the power of 4 times 3. Okay. All right, so the question is now, one of the factors, how many factors does it have? Now, something that all students should know, I don't know whether I've done that, but I think I did, I'm not sure. This is very important. The number of factors is equal to, I think I've done this. You increase each of these by 1 and multiply them. When you factorize it as a power of primes, as we have done, this is 16 times 3, which is 2 to the power of 4 times 3. You look at the exponents. You increase the exponents by 1 and multiply them, and that gives you 10 factors. Okay, so now what is the probability that the chosen factor is not a multiple of 4? So you have just 10 factors. So all you do is you can list the 10 factors if you like. I can do it. 148, 224, 316, 412, 6, 8. So these are your 10 factors. If you go on now, the next one will be 8. 8 times 6, we already got it. So these are your 10 factors. And what is the probability that this is not a multiple of 4? Then you eliminate all the multiples of 4. And those are the multiples of 4. And how many do you have? You have 5 of these are not multiples of 4. And you have 10 altogether. So the probability...
Prof, you forgot 4.
Huh?
You said 4 is not a multiple of 4.
Oh, I said 4 is not a multiple of 4 as well. What am I doing? I'm not... Oh, I see. We're looking at those which are not multiples of 4, even that one. Yeah. Okay, so this is also a multiple of 4. I should have eliminated that 4 as well. Thank you for that. So the number of factors which remain, which are not multiples of 4, are 4 of them, and there are only 10 factors. So the probability is that is 4 over 10, which is 2 over 5. And so you can say the probability is 2 over 5, which is 0, 4. Probability is a number between 0 and 1. So the answer to this is 0, 4. Okay, guys, that brings us to the end of this. I want to thank Ellie for going on for half an hour beyond her time. I could have dismissed her, but I need her because she's so useful. Ellie, were there any questions which people raised in the chat?
Not for the last couple of questions, no.
Okay. So these are kind of challenging questions. And okay, any comments from the guys? What I want to tell you is that many of the problems we did here were post round 1 problems. You know, I'm very bad. I'm not a nice person. When I see problems which are easy, I don't like to look at them. So I ask you tough questions so that you stretch your imaginations and think. And it doesn't really matter because in the end, you will learn a few tricks. Today you learn a few tricks. Like for instance, you learned about isosceles triangles and the vertex lies on the perpendicular bisector of the opposite side. That's an important one. You also know that when you got the midpoint of an hypotenuse, that point is also the center of the circle. Those are two useful things that you learned. And yeah, so there are other things. Probability. What do you mean by probability? You look at the successes, the number of times you get a odd factor, 1, 2, 3, 4. There are only 4 odd factors altogether. I'm sorry, 4, which is not a multiple of 4. And the number of successes over the total number altogether, that's what you mean by probability. So here you got 4 successes, only 4 times this happened. So that is what you mean by probability. And then you can work out questions on probability like that. The number of successes over the total number of possibilities. Okay? And then we saw the pigeonhole principle, where you say if you got 370 trying to fit into 365, cannot happen. Some of those will have to be repeated. So that tells you it's a general principle. If you've got m pigeons going into n holes, and m is bigger than n, you've got fewer holes than pigeons, then one of those holes will have to have at least 2 pigeons in it. And you have a lot of applications for that, very beautiful applications. And if you want to know more about that, go into the book and Google, or at least put control, find pigeonhole principle. You'll find half a dozen problems there, and go and have a look at that, and you'll see some very nice applications of this principle. Okay. Well, thank you very much, guys. If there are no further questions, the class can now be dismissed.